Welcome back to ECE 442-542. We are picking up in the middle of Unit 3, and homework number 3 is due in a week, March 2nd, and that will be using material that we finish up today and probably the next time, which is Wednesday. But in between those, I've given you some additional notes on how to inversely transform when you have complex poles. And you might look at those and make sure that you're clear on how to do that. When you have complex poles, now you have exponentially weighted sines and cosines. Whether those exponentials are growing or contracting depends on whether they're outside or inside the unit circle. But if you have exponentially weighted sines and cosines, you now have complex poles. Or if you have complex poles, that corresponds in the time domain to exponentially weighted sines and cosines. That you need to make sure you're clear on, and there's some extra notes in Unit 3 discussing different ways of doing that. You can play with complex numbers, or you can play with real coefficients. There's two different paths, and they are equivalent ways of obtaining inversely transforms when you have complex poles present. Just as a reminder, our second exam, we do have one, and it's scheduled for the 25th of March, which is in about a month. And in between that is actually spring break somewhere. So if you've seen the tents, that indicates we're getting close to spring break on campus. They're setting up for the Festival of Books. Hopefully you'll be able to navigate your way through the maze. If you're online, I guess it doesn't mean anything, but you might want to start setting up some tents in your home or in your apartment just to give yourself the same feel of that navigating path to the class. What we will do today is we will review or recap or reintroduce inverse Laplace transforms, just so that we start to feel comfortable with the same kinds of processing steps can be used to obtain the inverse Z transform. And in this case, we also want to make sure that we are connecting the transform together with the appropriate region of convergence. If you have a causal sequence, then you know that the region of convergence is beyond all of your poles. If it's anti-causal, your region of convergence is inside all of your poles. If it's two-sided, you have some poles inside and some poles outside your region of convergence. And if it's right-sided, which is a generalization of causal, if you have some negative indexed terms, then you need to remove that limiting case when z goes to infinity. Converse to that, if you have a left-sided sequence, which now you might have a finite number of indexed terms in your sequence that have positive indexes or indices, then you have to eliminate that extreme point, which is z equals 0, that is in your general disk of a region of convergence. That then is your removal of these extreme points, and we will also talk about bounded response and unbounded response, and those can occur for any of these different cases. You don't have bounded when you always have, if it's causal, you don't always have bounded. No, you can have unbounded and bounded. If it's anti-causal, you can have unbounded and bounded. If it's two-sided, you could have bounded and unbounded behavior in those different scenarios. We will then, yes, question? No, I'm meaning, so here I guess I should have said unbounded response. So you have an bounded response or an unbounded response. The bounded and unbounded in this short discussion was referring to the time sequence and not to the region of convergence. So the region of convergence, when it goes unbounded, is in what case? The causal case. And when it's right-sided, then it's actually bounded. But in that, I should have said a bounded time response or an unbounded time response can be seen in any of those region of convergence cases, whether you have a causal case, an anti-causal, or its modified version, or a two-sided or an annular region of convergence. You can have a bounded time response or an unbounded time response for any of those. We will then talk about why we can start saying, why is stability concerned with the notion or the concept of having our poles inside the unit circle. We usually are referring to a system that has a causal impulse or pulse response. Question? When are we going to see the grades for homework 1? Or exam 1. I had to correct because you had to correct, right? So when are we going to see the grades for exam number 1? How long can I keep you in suspense? One more day. So hopefully after class I will have time to go back to my office and upload the grades. I will try to return the exams after class. Okay. In homework 3, if there is not a MATLAB section, you won't have MATLAB in homework number 3. Finally, unit 4 will be discrete equivalence. How do we go from a transfer function that describes an analog system to a transfer function that describes a discrete system? For example, if you now have a low-pass filter, an analog low-pass filter, can you immediately, using a discrete equivalent strategy, come up with a transfer function for a discrete time system? And if you do, you now know how to create a difference equation, and now you can just turn the crank and put that into a computer or a microprocessor. Now you can build low-pass filters, high-pass filters. If you have some analog G of S, will learn how to find discrete time G of Z's using different discrete equivalent strategies, and that's unit 4. At the end of that, we have exam number 2. When will you see the exam or the scores for exam number 2? That's a very good question. After you've completed exam number 2. I don't have a way of forecasting that. And hopefully, based on your exam 1 performance, if that wasn't as strong as you would like, I won't be able to extrapolate what you would get in exam number 2. Hopefully it has a much higher score. That's what I'm saying. All right, let's revisit or refresh or recall inverse Laplace transforms. If I now said, let's start with this particular example, 6 over s plus 2 and s plus 3, what would be a partial fraction expansion structure that I can put on the right-hand side of that equality sign? And just to mix it up, I'm going to use C's and D's. Okay? Has nothing to do with your grade on exam 1. I don't want to hear that question, okay? But I don't know. I have C's and D's today that we're going to be talking about. If this is now the structure of the Laplace transform, and here we're assuming we have right-sided or causal x of t, or we're looking for little x of t for positive time, t greater than or equal to 0. Can you now write down the structure for x of t based on C, D's 2 and 3? because you know the poles are at -2 and -3. Those are the values of s that cause those denominators to vanish. Those now give you your modes, e to the -2t and e to the -3t. So now we have d weighting e to the -3t, and that's now t greater than or equal to 0. How did you normally do that? Did you use the cover-up method? And maybe you didn't call it that, but the cover-up method really is, and I can't illustrate it here necessarily, but you can on your own paper. Let's say that you're trying to now solve for the c coefficient. You essentially cover up the s plus 2 factor on the left-hand side and evaluate what's left at the value of s that causes the s plus 2 factor to vanish. You're really multiplying everything through by the factor s plus 2 and evaluating at s equal -2. But some places or some authors refer to that as the Heaviside cover-up method. If we now cover up the s plus 2 factor in the denominator and evaluate that at the value of s that causes the factor that we covered up to vanish, now we end up with 6 over -2 plus 3. And I guess today I can actually compute 3 minus 2. That gives me 1. I'm dividing by that, or this is now 6. I've now found c. The cover-up method, if we have distinct roots or distinct poles, allows us to individually or independently find these unknown coefficients. So it's a clean way of doing it. You don't end up with coupled equations. D can be done similarly. Now we cover up the s plus 3 factor that was sitting underneath d on the left-hand side. We now have 6 divided by -3 plus 2, or now we have -1 dividing into 6 to give us d equaling -6. Now we have the specific x of t that we were after. We now have 6 e to the -2t minus 6 e to the -3t for t greater than or equal to 0. Or we could do that same expression using a switch, where u of t is now the unit step, and it's on when the argument t is greater than or equal to 0. That allows you now to write it without having to say comma t greater than or equal to 0. And it might be cleaner when we start talking about double-sided things to be able to switch different pieces of the expression off and on for different ranges on our index, in this case t. If you have an inspire, or if you want to get inspired, you can just look at this. You can now use the expand function, and it will do the partial fraction expansion for you. I simply did the controlled division, and that now puts it over this ratio instead of looking at this one line kind of messy looking expression. Now you can say expand 6 over these factors s plus 2 and s plus 3, and hit the enter button and you get what you needed. 6 for C and -6 for D. What are some other methods for finding C and D? The reason I'm doing this is because you can do this same kind of thing once we start talking about inverse Z transforms for discrete time transfer functions. That's why we're reviewing this. These strategies, though, might actually lead to coupled systems of equations. What if we now did a common denominator approach to trying to find C and D? Here we're saying, oh, we still have C over S plus 2 plus D over S plus 3. But now what we can do is we can put those back over the same common denominator. And if we do that, then we have to scale C by the factor S plus 3, and we scale the D by the factor S plus 2. And now we can start equating. Well, maybe let me do one more step. Let me distribute C and D and combine so that now we have C plus D scaling S, and we have 3C plus 2D scaling S to the power 0, or that's our constant term. We can now equate coefficients in the numerator. We can equate this with that. Which tells us, or gives us what? Now we can see that there's no S term in the original expression. That forces then C plus D to equal 0. That's from the comparing the S1 coefficient. And the constant coefficient, or the S to the 0 coefficient, says that we now have 3C plus 2D equaling 6. And we can now put that into a matrix, if you like matrices. We now know that C plus D equals 0, and 3C plus 2D equals 6. And if you solve that coupled set of equations for C and D, or if you invert the matrix 1, 1, 3, 2, you better end up with the same C and D values that we had doing the Heaviside cover-up method. That's the common denominator approach. And sometimes that's the way to try to find these unknown coefficients in your expansion. Convenient values of S is another strategy. What makes for convenient values of S? What S values are not convenient, or what S values can you not use in this approach? You can't use the values of S that cause the denominator to vanish. Then you would end up with infinity equals infinity, and that doesn't give you any useful information. So if we have 6 over S plus 2, S plus 3, we know that we can't have, or we can't use as a convenient value, we can't use minus 2 and we can't use minus 3. But we can use 0, since that's not minus 2 and minus 3. That now says that we can say, oh, if I plugged 0 in everywhere for S, I would have 2 times 3 downstairs, or 6 over 6. And if I do that in my partial fraction expansion, that I had C over S plus 2 plus D over S plus 3, and now I can do something like I did before. I can put those over a common denominator, and now I have one equation relating C and D. I need a second one, so I need a second convenient value of S. S equal 1. I plug in S equal 1, something that's convenient. And in this case, minus 1 was my convenient value. And I now am able to, in this case I have 2c plus d equaling 6. And I also have 3c plus 2d equaling 6, and I could set that up as a system of two equations and two unknowns. I have 3c and 2d and 2c and 1d. Oh, and the reason I can just compare numerators is my denominators in both cases were the same. Here I had a 2 and a 2, and here I had a 6 and a 6. So that allows me to just focus on the numerators. And I then have, for the second equation, 2c plus d equaling 6 as well. Again, you could solve that for c and d. For a 2 by 2, it's not that hard to find the inverse, and you can quickly find what c and d need to be, and those, again, would be the 6 and minus 6 as we found consistent with before. That's our review or refresh of Laplace. Now let's look at applying something similar to the inverse z transform. Let's say we now are asked question.
Question for the previous question. Would it matter if like 1 times 2, would it matter if it's like half times 4 or any other number? Because it's not like a placeholder variable.
So now I'm not quite sure I'm understanding your question.
It's 6 over 2, right?
So the denominator, well, the expression on the left is 6 over 2.
The final answer we got 2c plus d over 1 times 2. That 1 times 2 comes from 2, right? The denominator.
Well, the 1 times 2 comes from obtaining actually a common denominator of the denominator of c and the denominator of d. So now you have to make sure everything works out, but you could have said, oh, 3 is equal to c plus 1/2 d if you wanted to. That would give you a consistent expression. But you have to make sure that the 1 times 2 is actually the denominator piece under c times the denominator piece under d. We were getting a common denominator from those two denominators. The question was, I think, related to how do I manipulate that, or how does that arise? I hope that helped. It's important to feel comfortable with that because we're going to be doing something similar for the z transform, but it has a little bit of a hiccup. We can't just do it directly. So we're going to see how that plays out as we work through this next example. Let's now find the time domain sequence f of little n given the following transform expression for capital F of z and the region of convergence specified by the magnitude of c, the magnitude of z. I have c's and d's on my brain, don't I? I was recording, no, I won't say anymore. So magnitude of z is bigger than 3/4. Hopefully, you know that the structure for the time sequence, little f of n, is made up of the two modes given by the values of z that cause your denominator to vanish. We have one mode as 1/2 to the n, and the other mode is 3/4 to the n. Can we say anything more about that structure based on the given information? Can we say what little n this is valid for? Is it for all n? Is it for negative n's? Is it for positive n's? Can we say based on the region of convergence? Or if we can't, let's now go start drawing pictures. we can think maybe a little bit more clearly if we draw a picture. Here's our picture of the z-plane. We have the pole at 1/2 and the pole at 3/4. Those are our two modes. And we were told where was our region of convergence. We say z is bigger than 3/4. We now know that our region of convergence is shading everything outside of this open void of radius 3/4. That means that we actually can have something going off to infinity, which if we were doing f of z and we had something like f of minus 1z plus f of 0 plus f of 1 z to the minus 1 in that series expansion, which was this infinite expansion, and we know that the region of convergence can go off and include going off to infinity. What does that tell us? Does that tell us any useful information about some of those coefficients that are scaling the z's? It now needs to be causal, doesn't it? Our little f of n. We now know that this has to be 0, as do all of those other coefficients. This now says that this is n greater than or equal to 0. We did that drawing of the picture with the region of convergence to try to remind us of when this particular little f of n was valid. It's valid for n greater than or equal to 0, or it's a causal sequence. What can you tell me now if I ask about the bounded nature or the unbounded nature of little f of n? Can you tell me the time response?
I would say little f of n is bounded in the time domain because the ROC lies on the unit circle.
So you can argue for what it is based on many different arguments. One argument is the unit circle is contained or lies on the region of convergence. That, we said, corresponds to a bounded behavior in the time domain. You can also directly look at the expression and say, oh, if this is true for n's non-negative, I have 1/2 to the first, 1/2 squared, 1/2 cubed. I have 3/4 cubed, 3/4. That's contracting. That also allows you to say, just by direct inspection of f of n, that f of n is bounded. And it's nice, in fact, when you can start looking at this from multiple directions and getting consistent results. You could also say, which was mentioned in the response to is f of n bounded, the response was, well, our region of convergence includes, bless you, the unit circle. And both of those are valid ways of arguing that little f of n is bounded.
In this case, the RC is not bounded, right?
The region of convergence is going to infinity. The region of convergence actually goes all the way out to infinity in all the different directions, along the real line, at a 45-degree angle, at a 10-degree angle, at a 90-degree angle. It's going off to infinity. So the region of convergence is unbounded or unrestricted. I guess it's confusing that I say bounded for two different ways, but I hope that you now start to get comfortable with holding those different bounded and unbounded ideas in your head at the same time. The benefit of taking this class. You can talk about bounded time domain waveforms or sequences resulting from an unbounded region of convergence. Now, if you looked at your Z-transform table, now or on the exam, you might see this pair. You might say, oh, in the frequency domain column, that's what this Z is supposed to be representing. Here's now the frequency domain column. And here is the time domain column. If you knew alpha in this transform expressions, alpha z over z minus r, you could immediately write down what the time domain is if you know the region of convergence is outside of capital R. You now know it's alpha r to the n for n greater than or equal to 0. What if now somebody gave you an f of z equaling z over z minus 1/2 times z minus 3/4? And you said, oh, this is a piece of cake. Let me just do a partial fraction expansion. This is what we learned in our third year, in our junior year, right? Maybe 320. In terms of Laplace, now it's a over one of those factors, z minus 1/2, plus b over z minus 3/4. But now what do you see, or do you see an issue with the comparison of this and that? If we needed to compare those, do they directly compare? We're missing a z, aren't we? We're missing a z in the numerator, so these two are inconsistent. So we can't just go whistling off and saying, oh, let's just do a straightforward or direct Z-transform. We won't have the right pair in our Z-transform table that we're looking for. We won't be able to immediately write down the time domain expression from after we found the A and the B. If we do this for our partial fraction expansion, a strategy for finding capital or little f of n from capital F of z. So what do? Well, we just pull a fast one. We say, well, if that doesn't work, why don't we expand f of z over z in a partial fraction expansion? Then let's see what happens. Suppose that I now have this. F of z over z is equal to 1 over z minus 1/2 factor times z minus 3/4. This now I could say, oh, well, that's just some a bar over z minus 1/2 plus a b bar over z minus 3/4. And what we're doing now is we're focusing right now on this piece of the problem. We find a bar and b bar based on what's highlighted in yellow. So what is, if that's the case, and we found a bar and b bar, what's f of z?
A bar z over z.
That's now in the table, isn't it? That's the structure we need. We now have a z over z minus r plus a z over z minus r sub 2, where r sub 2 is 3/4 and r sub 1 is 1/2. We can now immediately go into the time domain. We now know that f of n, little f of n, is going to be a bar 1/2 to the n plus b bar 3/4 to the n for n greater than or equal to 0. That means we need to focus on doing our cover-up method based on f of z over z to begin with, and then we find our coefficients that we need to produce the time domain expression. For example, what's a bar? Well, now we go here and we say, oh, I need to cover up the z minus 1/2 factor and evaluate what's left when z is equal to 1/4. Pardon? Oh, 1/2. I can't see. Can't hear either. I'm suffering. But we have a z minus 1/2, so it would be when z is equal to 1/2 when we cover that up. Or we now have a bar is 1 over z minus 3/4 evaluated at the value of z equal to 1/2. A bar is now minus 4. Likewise for b bar. We cover up the factor underneath b bar, which is the z minus 3/4 factor in the left-hand side, and evaluate that when z is equal to 3/4. We now have 1 over 1/4, or 4. That now allows us to write down what f of n is. The a bar was the factor or the coefficient associated with z over z minus 1/2. That's now the minus 4. The b bar was scaling or weighting 3/4. And that was when n was greater than or equal to 0. Why do we do that? Or why do we know that? Why do we know n was greater than or equal to 0? That was our drawing before, wasn't it? We were given the fact that our region of convergence was outside of 3/4. So we could do it different ways, but we could say, oh, remember the definition of the z transform. And the fact that our region of convergence was beyond 3/4, and it was all the way beyond, meaning one of these points could actually go off to infinity, and that forces some conditions on these coefficients that scale the z to the minus 1 powers. Or it now forces f of minus 1 to be 0. It forces f of minus 2 to 0. It forces all of these negative indexed sequences to be 0. That's the why. And if you were doing this again with your calculator, you would now want to make sure that you were expanding f of z over z. Not f of z. You would expand f of z over z, which was 1 over z minus 1/2 times z minus 3/4, and it will now do that for you. You'll now obtain the minus 4 for the A bar and the 4 for B bar. Now that we've looked at one particular region of convergence, let's look at a different one. What if we looked at an annular region of convergence? And we only have 2 poles, so there's only one possible way to produce an annular region of convergence for these 2 poles. Where's the region of convergence? Inside 1/2? Beyond 3? It's annular, you said. So that means it's between the 2. There's our region of convergence. It's between 1/2 and 3. And without even, you know the structure. It's 1/2 to the n and 3 to the n, because those are your poles. But can you tell me anything about what you would expect for the time response behavior of that sequence based on this picture? It's bounded because the unit circle is on or contained in the region of convergence. We have a bounded time domain sequence because the region of convergence includes the unit circle. And here's the structure. Now we can write it in one line. There's many ways of writing little f of n, but when is the first piece? What range of n or values of n are true for the first half of the f of n expression? N negative, n positive, n positive, n negative. It's switched on with u of n, so this is going to be for n greater than or equal to 0. And when is the mode associated with 3 to the n turned on? Only when n is less than 0, strictly less than 0. And that's now our bounded behavior. Let's now verify that. Let's go the other way. Suppose we start with something that has this structure, and let's find its z transform. And then we'll be able to essentially start going back and forth. Yes?
It's bounded in the frequency domain.
Where is it bounded? What am I meaning by bounded? This bounded,
Or is it just bounded for the 1/2?
this is bounded referring to the time domain response. The bounded behavior that I'm using bounded for there is little f of n.
Like, in terms of
The region of convergence is bounded. It doesn't go off to infinity. That's kind of a given in this case because it's what? Not going off to infinity. We have a bounded region of convergence, but it could be that the response associated with a bounded region of convergence could be an unbounded time domain response. That's not the case here. Let's now look at going essentially using strategies that you should be comfortable with from exam number 1. Let's now find capital F of z from this two-part little f of n. We have one piece that's on for n less than 0. We'll call that f sub 1 of n. And a second piece is on when n is greater than or equal to 0. We now want to find f of z, and we're going to do it using these two different pieces. Let's find it in parts. And the poles, those are not in the region of convergence. They never can be, can they? Our poles will never be in the region of convergence, no matter whether we have a disk, an annular shape, or a large region of convergence with a disk removed or a void in the center. I said large because it may not include infinity. This is what we're looking at. We're looking at f of n equaling f sub 1 when the indices are negative and f sub 2 when the indices are positive. And we're able to do that by switching those off and on by the appropriate unit steps. When is that switch on in this expression, in this z-transform expression for little f sub 1 of n? What do we know about the argument of that unit step? It's on when it's non-negative, isn't it? We now need minus n minus 1 to be bigger than or equal to 0. We can now add n to both sides. And now we know the index n is minus 1 or smaller. That's when this particular series has non-zero terms. When n is negative. So now we can sum this. We can say, oh, this is 2 times this sum from n equal minus infinity to minus 1. I factored the 2 out since that doesn't change for all terms. The 3 is scaled by n, and the z to the minus 1 is scaled by n. And here I've written z to the minus 1 as 1 over z. I now have 3 over z to the n. And I want to find s. And then I can scale it by 2, and that will give me capital F sub 1 of z. S now, going sort of backwards on the sum, is 3 over z to the minus 1 plus 3 over z to the minus 2. And we just keep marching all the way to the left in terms of our indices to minus infinity. When is this series expansion well behaved? What do we need 3 over z to behave like? So now we are effectively dividing we're dividing 1 by 3 over z, or 3 over z squared, or 3 over z cubed. What do we need to be in the denominator if we know that we want this tail to start getting smaller and smaller? We need that 3 over z factor to be bigger than 1, don't we? So this, to be well behaved, we want this to be bigger than 1, and this is our common ratio. And I may be doing this different than what we've done before, but I'm trying to do it a little different each time maybe, so that maybe one time it goes, oh, that now makes sense. Or I didn't think of it that way. Hopefully one of these ways it will start clicking. Now we can scale that original equation by that common ratio, 3 over z. And we end up with 1 plus 3 over z to the minus 1 plus 3 over z to the minus 2. You know what's going to happen. Now we compare those two, or we take the bottom expression away from the top. We now have scaling s 1 minus 3 over z. And when we compare the right sides, we're subtracting the bottom from the top. The top has exactly the same terms as the bottom, except the bottom has one more term, and that one more term is 1, and we're subtracting it away. So we end up with minus 1, or s is now minus 1 over the quantity 1 minus 3 over z. Or we could write it other ways. Minus 1 over 1 minus 3 z to the minus 1. What was our capital R? It was 3. And when was this being examined? For what indices? Negative, and now we have this minus 1 in the numerator. Or we could write it in terms of positive powers of z. We now have minus z over z minus 3. And s is bounded when? We said this guy needed to be bigger than 1, didn't we? That now allows us to say, if we multiply both sides by the magnitude of z, we now know that z is less than 3. Now our region of convergence is a disk. We know z, all the points in the complex plane z that are smaller in magnitude than 3 are belonging to our region of convergence. So capital F1 of z exists when the magnitude of z is less than 3, and what is f sub 1 of z? That's minus 2z over z minus 3, because that 2 we factored out. S was the minus z over z minus 3. And F1 was twice that. So capital F sub 1 of z is minus 2z over z minus 3. And here is our region of convergence picture. And sort of on the side over here is what's happening to our time sequence. And that time sequence is defined for negative n's, or it's anti-causal. Question?
So for the argument, what happens if you just use negative n instead of negative n minus 1?
So what happens, the question I think is concerning the switch. What happens if we just used u of minus n? What if we said, oh, well, I just need to turn it on for negative n? When is this going to be on? When is u of n on? So here's our question. What values of n allow this switch to be on? Now this could be on as long as the argument is 0 or bigger, right? So now we need, this is on when minus n is bigger than or equal to 0. Now we multiply that by minus 1, or we add n to both sides, however you want to do it. Now little n could be 0, and we don't want that particular 3 which scaled to n equals 0 would be 1. We don't want this piece to be turned on at n equals 0. So we need that argument in our switch to actually contain minus n minus 1 so that the switch is on when that argument is greater than or equal to 0, and that forces n to be negative 1 and smaller, not starting at 0. Does that answer that question? It might be a little bit odd to see that discussion there on the page. So now I'm saying, what about this as a switch? Does that make it, if you now go back in a week or before exam number 2, you come back from spring break, hopefully you haven't forgotten everything that we've covered before spring break. I know maybe if you're a graduating senior, you really want to go out with a bang for this spring break. Don't be too big of a bang, because you need to remember what's going on the second half of the semester. You need to graduate. Yes? Okay, you're saying D for done. Don't say that. Don't think that, right? Not that way. All right. Where were we? Let's scroll, keep scrolling. Now I've got you all thinking about spring break. Somebody's already looking up there on the website their plane reservations and everything else, their hotel reservation. All right. F sub 2. What was F sub 2? That was the 1/2 raised to the n. That was the mode. It was scaled by 4, so we're going to pull that out. And now, when was this true? Or when is this common ratio going to produce a well-behaved f sub 2 of z? The common ratio is 1/2 z to the minus 1, or it's 1 over 2 z. What do we need that? Because now that is going to be raised to the 1, raised squared, cubed, and we want that to be diminishing. In order for that to happen, we need this to be less than 1. Or, scaling both sides by the magnitude of z, now we know that z needs to be beyond 1/2. This region of convergence for this piece is unbounded. For this piece, what we're going to see is we have to have z true for both pieces. One piece is going out from 1/2. One piece of the region of convergence is coming in from 3. Their common intersection is the donut, or the annular region. That's how we will get the annular region. But here, what do we have? We now know that this will be 4 times 1 over 1 minus 1/2 z to the minus 1. That. And when is that true? That's true as long as z magnitude is bigger than 1/2. Or our region of convergence here and let me put a subscript 2 on that. Did I subscript the previous? Yep, I did. I said ROC1. So we have 2 rocks, rock 1 and rock 2. And which rock are we on? Third. From the sun. Do I have anyone's attention? Everybody's disappeared. They've already left for spring break, and we still have 3 more sessions before that. What's the overall region of convergence? Well, we need to make sure that the intersection of those two is what we use. We say, oh, region of convergence 1 was when z was less than 3. Region of convergence 2 was when z was bigger than 1/2. Their intersection gives us this annular region. And now is f of n bounded. Region of convergence doesn't include or includes the unit circle. The region of convergence includes, which now that says the f of n, the time domain sequence, is bounded. And f of n was actually two-sided. What if we looked at a different region of convergence? For this same set of modes, we have 2 poles, a pole at 1/2 and a pole at 3. What if we looked at this region of convergence for the magnitude of z living beyond 3? Now we have a void. We have the entire z-plane, except now we've drilled out this void in our z-plane, and we no longer include anything less than 3. Everything else in the z-plane is in our region of convergence. So this is another region of convergence for the same pole pairs. What's the structure of the response? If I just gave you this on exam 2, could you give me the structure of the response? I'm waiting. Yeah. What is the structure? If I just scroll down, or if you already have it printed out, you know, right? It's this. Alpha 1, 1/2 to the, it's the mode at 1/2 and the mode at 3. We know that's our structure. What we may not know is when, n-wise, what values of n is this defined for? Can we tell from the region of convergence? And if you can't, then you start saying, well, what would I call this? W. So now I know my W of z question?
So from this picture, if you have the z-plane, you cannot tell directly if it's causal or non-causal. You have to have the n.
So now, if this is the picture for our time domain sequence, or we're given frequency domain information, we're given the poles and we're given the region of convergence. From that information, can we tell anything about the little n that this little w of n is defined for? That's what I'm trying to do now. I'm trying to sketch that out. I've said, oh, I know capital W of z, if it exists, has this series expansion, a bunch of negative indices scaled by z squared, z, and then I get into the constant W of 0 plus then all the positive ones. W of 1, z to the minus 1. W of 2, z to the minus 2. Now I look at that region of convergence and I say if capital W of z is well behaved for all the z's in the region of convergence, can I find one of those region of convergence z's that will explain which of these pieces can't belong. Now I feel like I'm at Sesame Street. One of these pieces doesn't belong. Or pieces, right? Which piece or pieces do not belong? You now know that this piece right there could go off to infinity. Yes? And if you plugged in infinity here, what happens? You would get an unbounded W of z. It wouldn't be well behaved. That forces this to equal 0. And it forces all of these others to equal 0. Now you can conclude, based on this region of convergence pattern, the defining range on your little n's. When is this defined? This is defined now for n greater than or equal to 0. Now, based on that information, can you answer, is W of n bounded? Now just plug in some n's where they exist. You know n is 2, it's 3, it's 4.
Couldn't you also just reference the graph and say it's not, unit circle doesn't lie?
So now you could argue a couple of different ways. You could say, wait a minute, the unit circle is not contained or doesn't lie on the region of convergence. I know this leads to an unbounded time domain response. But I still don't feel comfortable with that. But now you go and you go, well, now my analysis tells me this. I plug in some n's. I go 3 squared, 3 to the 10th. Ooh, that's going crazy. The 1/2 is well behaved, but all I need is one mode that's not behaving and things are unbounded. So this now tells me my answer the second way. This now says Wn is W of n bounded. No. Yes.
Is it possible you could have like a W of n where the terms are growing in a way that they're both growing exponentially, but they're like subtracted, so it ends up being bounded, or does it always go unbounded? If you had like a 3 and a 2 to the n, but like you were like minus 2 to the n, somehow it was minus 2 to the n. So you had 3 to the n minus a.
Did everyone catch that? Can we have a combination of, so there the question was, and we can sort of be a little bit, what do I want to say, devil's advocate on this. If you had, really the only way that you could compare two would be to have alpha 1 and alpha 2 maybe being opposite in sign and your modes being the same, but then you would have had a coefficient of 0. But in fact, if you have a pole that's going to lead to a mode that's unbounded, you have to basically conclude that coefficient could be minuscule, but it's going to allow that unbounded behavior to grow. Now, where were we? W of n now goes unbounded as n marches off to infinity. Or, this is the other argument, unit circle is not included in the region of convergence. All right, now you're experts. Let's look at a generic annular region and see what you can conclude. Here's some observations. I have 5 different x's labeled 1 through 5. And I have an annular region of convergence. And I probably just broke my stylus, so we may be finished. But let's see. Let's now, how do we do this? Associate the poles larger than the annular region or beyond the annular region. So now, which poles are beyond or larger than our annular region? Five is also beyond. We can't neglect things in the left half plane or above us. It's now determined by radius away from z equals 0. So we now have poles 1, 2, and 5. That now corresponds what? The region of convergence is inside them. That's where we were able to conclude negative arguments or negative indices, little n being negative. Or the region of convergence is interior to poles 1, 2, and 5. And if somebody labeled those specific poles or gave them specific locations, you would now say, oh, pole number 1, let's say that's at 2. That's 2 to the n. And we know what n is defined for. N is now negative. And the poles smaller than or interior to the annular region are which poles? 3 and 4. So now we have poles 3 and 4, and those now correspond with n greater than or equal to 0. Or the region of convergence is exterior to poles 3 and 4. We have this picture. What could we say now about the bounded or unbounded behavior is summarized in this statement, statement B. If the region of convergence includes z equal 1, then the time domain sequence, one-sided or two-sided, is bounded. In this case, for this annular region, what do we know is true? Do we have a two-sided or a one-sided? Two-sided, because we had some poles that were defined for n negative, some poles defined for n non-negative. So we had a two-sided, and this picture, can we say what the time domain sequence is going to do? From this amount of information, can you tell me what, let's call it x, little x of n looks like? Is it bounded? Is it unbounded? Can you tell me? From this picture, what can you tell me? Or what if we said, what if I did this? I now said little x of n is r1 to the n. That one corresponds to pole 1. And let's call that alpha 1. This is now alpha 2. Wait a minute, which ones were which? I better get my picture back. 1, 2, and 5. So let me now say alpha 2 R2 and what do I scale those by? Switch those with. Is that the right switch? I said these are defined for n less than 0. Plus alpha 3 R3 to the n plus alpha 4 R4 to the n. Does that look okay? Can you tell me the bounded or unbounded behavior of this? You can't until I tell you what some of those r's are equal to. Yes? I have to now label this a little bit more specifically. I have to show you where the unit circle is. If the unit circle was here, what could you tell me? Bounded or unbounded? If the unit circle was here, bounded or unbounded? Bounded. And if the unit circle was here? Great circle, isn't it? It would be unbounded. You getting the hang of this? You can have all sorts of bounded, unbounded time domain responses for a generic picture.
So the numbers 1, 2, 4, and 5 are not like basically the radius.
The 1, 2, 3, 4, and 5 I didn't define, did I? Those pole locations. So it was unclear until somebody shows you where the unit circle is at.